Hi, I'm GUO I'm 15 years old, secondary 3 for NS High School. In this lesson, we'll be taking a look at physical chemistry. And in this lesson of physical chemistry, let's take a look first. What does physical chemistry on its name states? Physics and chemistry, right? Alright, so now we take a look at how each can be related. So generally what you will hear is the math is the basics of physics, and physics is the basics of chemistry. And so, in this series, we would relate or link all these three subjects together: mathematics, physics, and chemistry. And you have different types of laws or different types of areas from each of these three subjects that you could use to link them together. Let's say kinetic molecular model, kinetic molecular theory, whatever you like to call it. So that can be used in both physics and chemistry, or let's say Graham's law from chemistry, or Maxwell-Boltzmann velocity distribution from physics. And of course, there are different types of statistics that could be very useful from math, let's say normal distribution. So these things all can be linked together in some way. So the focus for these few lessons is going to be the Maxwell-Boltzmann velocity distribution. Right, so when we start off this, what we're going to say in this lesson, first things first, we have to make a few assumptions. Since without assumptions, or let's say an ideal space, nothing is going to be easy. Everything is going to be complicated. You have to consider many different factors, and that is going to affect the final result you have very differently. Right, so the first thing is we will assume that the space we're using is isotropic. So what does it mean by the space we're using is isotropic? That means, let's say you have a particle and it's moving. So no matter from what direction you measure its velocity, for example, it is never going to change. If it changes, then that is not going to be isotropic. Let's say in this area, for some reason, it is faster, although you apply the same amount of force or something. So that is not going to be isotropic. So it is going to have the same physical property throughout the entire space you're using. And that is the first assumption. The second assumption that we're going to make is negligible, let's say, gravity. So everything on Earth, on different planets, on the sun, they all experience gravity. But when we are taking a look at the space we're using, we would assume an ideal environment for this experiment. So we would be ignoring the gravitational force, since it could be that little that it doesn't really matter. But of course, if you really want to say, yes, it does matter, like let's say it pulls it down a little bit and changes it. But of course, in the ideal case, we are not going to factor in gravity and other natural forces. Let's just put it in that way. So these are the first two assumptions. Then we'll be moving on to a third assumption. So when we're talking about velocity, let's say in one dimension, you only have one way. In two dimensions, you have an x-axis and a y-axis, or x component and a y component, or however you like to put it. While in three dimensions, which is what we'll take a look at now, you would have three different components. So let's say there are Vx, Vy, and Vz. So these three different components, they are independent of each other. So what does it mean by independent of each other? Well, independent of each other just means that they are in no ways going to affect each other. Which, let's say you have a change in Vx, that is not going to result in a change in Vy or Vz. And the same thing goes for Vy and Vz. they are not going to change the other components. And that is what it means by they are independent of each other. Right, so these are the three assumptions that we are going to make. So then you could gather a few information from what you are going to have here. Let's say, for example, since this you have x, y, and z, that means a unit of it would just be, let's say, dx, dy, and dz, or you can also use a v form of it. Alright? So let's think about it again. We have Maxwell-Boltzmann velocity distribution. Now what is this exactly about? So in a space that you're going to have, if you put in many different particles, or rather of the same type but at different places, they could have different velocities, right? So what you're having is, what is the chance of you taking a particle out and it is of that certain velocity that you're thinking of? So those would be about probability, right? So what exactly are we trying to determine over here? So let's just say we have this thing called fx, or fv as a matter of fact. So fv, of course, you could take its vector, which is, you could just have a velocity, but here we are just taking the value of it, which is its speed. So this is that probability, alright? So you could call it that probability function or whatever you like, alright? So fv, what are we going to have over here? So of course you could change it into f square root vx square plus vy square plus vz square. So this is v in its component form, which you have these three components. So by Pythagoras theorem and stuff, you would get this. Since we have our third assumption, they are independent of each other, so you could also write them as these three different functions, since they're just independent of each other. So this is what we are going to be taking a look at. Right, now keep in mind that v, you are going to have three components. So it's just like, let's say you have a function of x, y, and z. So it is pretty much in the same way, three components. So when we differentiate it, are we going to use a normal differentiation, or are we going to use partial differentiation? Well, of course, since you have more than one component, which you can take it as a variable, you are going to use partial differentiation. So how is the partial differentiation going to work over here? So first of all, we could take a look at partial fv, partial vx. Now, there are two ways going about to solve this kind of thing. So the first one you can use is something called total differentiation, if you can recall what that is. So now what does total differentiation do? Now you're going to have dfv dv. Since here your so-called variable is v, so you just have it according to v. Well, the next part is going to be partial v, partial vx, since v is a composite or a function of vx, vy, and vz. So again, this is using total differentiation. So the next part that we're going to have, the first part, do you think you can solve it? We're not given the function, so we can't exactly solve that at this point. Then you take a look at here. So v, when you express it in its components form, you are going to have this function. So you just have to use chain rule to differentiate it. Now what happens when we use chain rule to differentiate it? Now this entire thing to the power of half. Well, differentiation, you're just going to have Vx over V. Then this part stays the same. Alright, so this is what you are going to have. Now of course, you can choose to change its form a little bit. Now what do I mean by changing its form a little bit? So you could take the first part and the last part as an equation. So how does it work taking it as an equation? 1 over Vx. So let's just say you divide this to the other side. And you're going to have partial Fv partial Vx being equal to 1 over V dFv dV. Now what can you think about when you look at this form? Are any parts of it not affected by Vx, Vy, or Vz? Which parts are affected by Vx, Vy, or Vz? So then you could think about, wait, what if I do this for, let's say, Vy? So in Vy, again, you're going to have this part. It's not going to change. Then if you look in this portion over here, the right-hand side would actually stay the same. So that means this is also equal to 1 over Vy partial Fv partial Vy and equal to 1 over Vz partial Fv partial Vz. Right, so these are what is going to equate with each other. So at this point, that is a first way of finding partial Fv, partial Vx. So what exactly is that second way? Partial Fv, partial Vx. Now this second way, you're going to take a look at this portion behind here. So since they're independent of each other, that means you could take these two as just a coefficient when you're solving it. Since when you change Vx, it is not going to affect the others. So these two parts behind, you're just going to take it as a coefficient. So it is just going to be F Vy F Vz and D F Vx D Vx. So this is the part that you are going to see. Now, how about you compare these two parts again? Is there going to be any similarities you see? Well, of course, you might find this part is just these two. So what if you substitute this portion into here? So what are you going to receive? So what you're going to have here is 1 over Vx. So then you'll have F Vy F Vz D F Vx over D Vx. So then you can also repeat the same for the others. Now how are the others going to work? So 1 over Vy. Now if you have realized, only the part with y is going to get differentiated. So that means Vx and Vz is going to remain untouched, while Vy is the part that is going to be differentiated. Here, and then you can do the same for z. Whoops, here is f. So this is what you are going to have. Alright, at this point, can you think of anything else? Well, of course, you can also equate it back to this part. Yes, you can. But when you take a look at these different portions, and you take a look at the original part that you are going to have, so how about we let something? Now let's divide all of this by this part over here. So what are you going to have? So that means you are going to see 1 over Vx f Vx. Then here is df Vx dVx. So this would be equal to 1 over Vy f Vy d f Vy dVy, 1 over Vz f Vz df Vz over dz. So what exactly are we letting this be, since here we used let? So when we consider this again, they're all equal to one thing, and this v would then have another 1 over 1 over fv. So how about we just take that as an a, which is just a constant, alright? So what is going to happen from letting that be a constant? What if let's, for now, just take one part of it? Let's say, well, only take a look at this part is equal to a. What exactly is going to happen? You're going to see, let's say we change this and we look at it like a differential equation, a separable differential equation, in fact. So you're going to have df Vx over fVx. Now if you wonder how this works, you just have this here. You can multiply Vx and dVx to the other side, and this is equal to a Vx dVx. What do you do here? You would integrate both sides. So when you integrate both sides, you're going to see ln fVx on the left side, and on the right side you're going to have a over 2 Vx square plus c or plus v or whatever you want. Of course you can choose to use different things, alright? So this part here is completely up to you, and you can also choose to write where c is an arbitrary constant. So this is what you see for most integration questions, where you would always have where c is an arbitrary constant since integration. Now you might be wondering, wait, if I have an arbitrary constant on the right side, do I need one on the left side? Of course you have, but who said you couldn't combine both arbitrary constants? So when you integrate both together, you could just have one arbitrary constant, since it is both arbitrary constants together, alright? So afterwards, you could have take the exponential for both sides, and you're going to have f Vx is equal to e to the power of a over 2 Vx squared. What happens to this plus c? So plus c is just times e to the power of c. C is a constant, so e to the power of c is another constant. So b, let's just say we let that constant be b, alright? So this is what we are going to see. But what else is there that we have to do? Of course, we would need to determine what b is. Now, how are we going to determine what b is? Firstly, you need a little substitution, which is let a be equal to negative a. Now, you might be wondering, how is this ever going to change anything? But when you substitute this inside and later on you try the integration, you would realize the power has to be negative, since if it is positive, it is just going to be bigger and bigger. So you have the convergent and divergent, okay? So only when this power is negative, then it would have a tendency to a certain value. Right, so what exactly is this integration that I'm talking about over here? So now let's think about this again. What is FV? FV is the probability. So probability, what happens if you have every single option, you add the probabilities together? That becomes a 1, right? Yes. So now think about this. I said that already. 1. Now what comes to your mind? So that means if we have this thing added up from negative infinity to infinity, so this part over here, if we have from negative infinity to infinity, that means this is going to be equal to 1. Alright? So, since this is probability of every single choice, you can't just have one choice gone or an extra choice and you have another way to choose anything. And of course here, oops, I missed out the dx. dvx. Alright, so this is what we are going to see over here. Now, does this integration look anywhere familiar to what we have done before? Well, because if it doesn't, then let's take a look at it. Let's divide b to the other side. Since b is a constant, and this is just constant, which is a coefficient of what we are going to integrate. So 1 over b, it is not going to do anything in this integration. Right, so 1 over b is going to be equal to, now, negative infinity to positive infinity, we could take the double of that, since if you actually draw this out, you're going to find something that, well, I'll let you figure it yourself of why we could just double it. So this is equal to 2, and now 2 what else? I'm going to leave a blank over here, and this is 0 to infinity, positive infinity if you really want to insist. Then e to the power of negative a over 2vx square. So here, d, what are we going to change our vx to? We're going to change it into square root a over 2vx. So when we have this inside changed, of course we are going to have something on the outside, which is square root 2 over a. And this is what we're going to see. Now, does this part still not seem familiar? Well, if it doesn't seem familiar, what you are going to have is 0 to infinity, e to the power of negative x squared dx. We have done this integration before, so you can go back to previous videos to watch. Like, for example, we have the double integration of how to solve this question. Alright, so the result of this is actually square root pi over 2. Alright, you can go back to previous videos to find out why is this square root pi over 2. How on earth are you going to get square root pi over 2 if it's actually infinity? So those questions you can go back to previous videos to find. Right. So we take a look back at what we have over here. It's the exact same form. So we are going to have square root 2 pi over a. And that means b is equal to square root a over 2 pi. So here we have found b miraculously. So what exactly are we going to do with b? So we could put it back inside here. So v f vx is going to be equal to square root a over 2 pi. And then e to the power of negative a over 2 vx squared. Now, keep in mind again, this is only vx. We want v. So what is v again? We take a look back over here. You have vy and vz. So what is it that we need to change? All we need to change is this for vy and vz. So it is 3 of those multiplied together, and we are going to see square root a over 2 pi cubed, since you have x, y, and z, and e to the power of negative a over 2. So this is going to be vx squared plus vy squared plus vz squared. So that means it is just going to be v squared. And this, if you know the Maxwell-Boltzmann velocity distribution, is actually of a similar form. The only difference is the a. So in future lessons, we are going to determine the a, but this is how you get the rough form of it. Of course, if you want to change this part into epsilon, epsilon is just mv squared over 2, which if you really want to insist on changing, so mv squared over 2, you're going to have a epsilon over m. Alright, so these will leave the form like this as of now. In the future, again, we would determine what a is. Like what you see with all those Boltzmann constant, you might be wondering what is going on with them. Just stay tuned for future lessons, and I hope you can understand what we have covered so far in this lesson. Alright, and thank you for your watching.